For the last few years, one company has become almost unavoidable: Nvidia. Its chips power the AI boom. They train the models behind ChatGPT-like systems. They sit inside enormous data centers being built around the world. And as artificial intelligence has become one of the most important technologies on Earth, Nvidia has become one of its most important gatekeepers. But in Beijing, a group of researchers has been working on something very different. Not a faster GPU, not a smaller transistor, not even a conventional digital processor. Instead, they went back to an idea the computer industry largely abandoned half a century ago. And according to their results, it worked. Their experimental chip reportedly matched the precision of advanced digital hardware while consuming roughly 100 times less energy. Under another configuration, researchers reported performance advantages, reaching 1,000 times that of an Nvidia H100 on specific mathematical workloads. 1,000 times. That number needs some context, because if these results eventually translate from specialized laboratory tests into real-world AI computing, this would not simply mean China had built another Nvidia competitor. It would mean something much stranger. The basic architecture behind modern computing may have a serious rival, and the technology challenging it is older than the digital revolution itself. To understand why this matters, you first need to understand how Nvidia became so difficult to challenge. The modern AI boom depends on an absurd amount of mathematics. Behind every chatbot response, generated image or trained neural network, are enormous collections of numbers being multiplied against other enormous collections of numbers, again and again, billions of times. For decades, computers handled calculations mainly through CPUs. They are extremely flexible processors, but traditionally execute instructions in a relatively sequential way. GPUs work differently. They were originally designed for graphics. A video game doesn't need to calculate one pixel at a time. It needs to calculate thousands of them simultaneously. So GPUs became extremely good at performing huge numbers of relatively simple operations in parallel. And neural networks happen to need exactly that. Nvidia realized the opportunity unusually early. In 2007, the company released CUDA, a software platform that allowed developers to use Nvidia graphics processors for general computing. At the time, this was not obviously revolutionary. Nvidia was still widely thought of as a gaming company. Deep learning was mostly an academic subject. The enormous AI industry we know today barely existed, but Nvidia was quietly building something much more valuable than a powerful graphics card. It was building an ecosystem. Researchers learned CUDA. Universities taught CUDA. Companies built software around CUDA. Engineers spent years learning how to squeeze more performance from Nvidia hardware. Then artificial intelligence exploded. Suddenly, almost every serious AI laboratory needed enormous numbers of GPUs. And Nvidia didn't just have the processors, it already had the software, the libraries, the tools, and millions of developers who knew how to use them. That advantage compounded. By 2026, estimates placed Nvidia's share of the AI accelerator market somewhere between roughly 75% and 90%. AMD was trying to catch up. Intel was trying to catch up. Google and Amazon were building specialized chips of their own. But Nvidia remained at the center. And once an industry builds itself around your architecture, replacing you becomes extremely difficult. Because switching isn't simply a matter of ordering a different piece of hardware. Years of code may need to be rewritten. Engineers may need retraining, and entire software pipelines may need redesigning. Nvidia had created something close to a technological fortress, but the fortress had a weakness. Not a business weakness, a physical one. Every conventional digital computer has the same basic problem. Data has to move. Numbers are stored in memory. The processor needs those numbers to perform calculations. So information constantly travels between the processor and memory. Compute, move, billions of times. This is commonly associated with the von Neumann bottleneck. And for ordinary computing, it was manageable. For modern artificial intelligence, the scale changes everything. AI models involve enormous matrices. They require huge amounts of memory bandwidth, and GPUs are increasingly hungry for electricity. A traditional data center rack might consume somewhere around 5 to 10 kilowatts. Modern AI GPU racks can consume 40 to 80 kilowatts or more, and newer systems continue pushing those numbers higher. Multiply that across thousands of racks. Then multiply it across hundreds of data centers. Suddenly, artificial intelligence isn't only a computing problem. It becomes an electricity problem, a cooling problem, an infrastructure problem. The International Energy Agency expects global data center electricity demand to rise dramatically by the end of this decade. Technology companies are spending hundreds of billions of dollars building the infrastructure required to support AI. And a significant portion of that investment isn't going into smarter models. It's going into keeping the machines running. Power plants, transformers, cooling equipment, transmission capacity, huge buildings filled with processors moving numbers back and forth. The strange thing is that computer scientists have understood this problem for decades. The industry simply found ways to build around it. Smaller transistors, faster memory, better cooling, larger data centers, more electricity. But another possibility existed. What if the computer didn't need to move all of those numbers around in the first place? And what if the mathematics could happen inside the memory itself? To answer that question, researchers had to reopen a chapter of computing history that most of the industry had already closed. Before computers became digital, many of them were analog. The idea is fundamentally different. A digital computer represents information using discrete states. On or off, 1 or 0. An analog computer represents information using physical quantities themselves. Voltage, current, movement, pressure. Instead of translating everything into binary instructions, you allow physics to perform part of the calculation. The principle is ancient. More than 2,000 years ago, the Antikythera mechanism used gears to model astronomical cycles. During the 20th century, analog machines were used for everything from military targeting calculations to aircraft systems. And for certain mathematical problems, they could be remarkably effective. Then digital computing arrived. And analog computing almost disappeared. The reason was precision. Real physical systems are messy. Voltages fluctuate, components vary, temperature changes behavior, noise creeps into measurements. A digital system only needs to know whether something represents one state or another. An analog system may need to distinguish between thousands of tiny variations. And as computers became more complex, those tiny errors became a serious problem. Digital computing was easier to reproduce, easier to scale, and far more reliable. By the 1970s, the contest was essentially over. Analog computing became a historical curiosity. A road computing had explored and abandoned. But not everyone stopped looking at AI. At Peking University's Institute for Artificial Intelligence, researcher Zhong Sun had been working on analog computing systems since around 2017. He wasn't trying to recreate the machines of the 1960s. The world had changed. More importantly, the materials available to engineers had changed. And the problem facing computers had changed too. Artificial intelligence was consuming extraordinary amounts of energy. Future wireless networks would need to process enormous numbers of overlapping signals in real time. Meanwhile, shrinking conventional transistors was becoming increasingly difficult and expensive. The old strategy was make everything smaller and wait for computers to become faster was no longer delivering improvements as easily as before. So Sun's team approached the analog problem differently. They made two important decisions. First, they used a technology called resistive random access memory, or RRAM. RRAM stores information by changing the resistance of tiny memory cells. The important part is that these cells can maintain their state even when power is removed, and because the information is represented through electrical resistance, calculations can potentially happen directly where the data is stored. Memory and computing begin to merge. The second decision was even more important. They didn't try to build a computer that could do everything. They focused on one problem: matrix calculations, the same category of mathematics sitting underneath artificial intelligence and advanced wireless communication. Instead of resurrecting analog computing as a replacement for every digital computer on Earth, they narrowed the target. One architecture. One mathematical problem. One enormous potential advantage: energy. But there was still a problem that had killed analog computing the first time: precision. Imagine trying to hit a bullseye in the dark. The traditional approach would demand that your first arrow land perfectly in the center. If it doesn't, the system has failed. Sun's team effectively asked a different question. What if the first arrow only needed to get close? Then you measure the error, adjust. Fire again, measure, adjust, repeat. Instead of demanding one perfectly accurate analog calculation, their architecture performs an approximate calculation quickly and then corrects the remaining error through additional passes. The first circuit gets close, the second helps refine the answer. Again and again, until the result reaches the required precision. It sounds almost obvious when explained this way, but it attacks the central weakness that helped kill analog computing decades earlier. Analog hardware could be fast and efficient. It just wasn't precise enough. So rather than trying to eliminate imperfection from the hardware, the researchers designed the system to compensate for it. And according to their experiments, it worked. On mathematical problems used in advanced wireless communication, the system reportedly achieved digital-level precision while consuming around 100 times less energy. When pushed further under specific benchmarking conditions, the researchers reported an advantage reaching roughly 1,000 times compared with Nvidia's H100. Which sounds revolutionary, but this is the point where the story becomes much more complicated. Because this chip has not destroyed Nvidia, not even close. The first problem is scale. A laboratory prototype and a production AI accelerator are very different things. RRAM cells are physical devices, and physical devices vary. One cell might behave slightly differently from the cell beside it. Those variations can affect precision. Correcting a few thousand cells in an experimental system is one challenge. Correcting enormous arrays inside commercially deployed processors is another. The second problem is software. Nvidia has spent nearly 2 decades building CUDA. Modern AI frameworks have been designed around digital hardware. Developers have spent their careers learning that ecosystem. An analog accelerator cannot simply arrive at a data center, replace the GPS, and expect everything to continue working. You need compilers, libraries, programming tools, frameworks, engineers, years of optimization. The hardware may exist before the ecosystem required to make the hardware useful. And then there is the biggest limitation: the headline number. The 1,000 times result did not come from training a frontier large language model against an H100 inside a commercial data center. The researchers tested specialized mathematical workloads, including matrix inversion problems relevant to wireless communications. Those are legitimate computational problems, but they are not the same thing as training one of today's largest AI models, and that difference is enormous. The researchers themselves have indicated that their next challenge is building a larger and more integrated version capable of solving more complicated problems. In other words, the experiment is impressive. The engineering is unfinished. So why does this matter? Because unlike many futuristic chip announcements, this one has two details that make it difficult to dismiss. The research was published in Nature Electronics. That means the methodology was subjected to peer review, rather than simply announced through a company press release. Peer review does not guarantee that a technology will become commercially successful. It does mean the results have been examined as scientific research. But another detail may be even more important. The chip was reportedly fabricated using a standard commercial manufacturing process, not an exotic material that only works under perfect laboratory conditions, not a one-off machine that requires an experimental clean room, a process compatible with the kinds of manufacturing systems already used by the semiconductor industry. That doesn't solve the scaling problem, but it changes the question. Instead of asking, "Can this exist?" researchers can begin asking, "How large can we make it?" And that question lands at a particularly sensitive moment, because the chip was not developed in Silicon Valley. It was developed in China. For years, the United States has restricted China's access to some of the most advanced semiconductor technology. The logic is straightforward. Advanced chips have become strategically important. They power AI systems, military technology, scientific research, communication networks, and increasingly, national infrastructure. Nvidia's most advanced processors therefore became more than commercial products. They became geopolitical assets. China responded by pouring resources into domestic alternatives. Huawei has developed its Ascend processors. Baidu and Alibaba have worked on specialized chips. Cambricon has built domestic accelerators. Chinese universities and state-backed laboratories have also expanded semiconductor research. Most of these projects attack the same problem directly. Build something closer to the GPUs China can no longer easily obtain, but analog computing suggests another possibility. Don't beat Nvidia by building a better Nvidia. Change the game. If digital accelerators are constrained by data movement and power consumption, then the alternative isn't necessarily a faster version of the same architecture. It may be a different architecture entirely. And this is why the 1,000 times number matters, even if it never survives contact with a real AI data center. It creates a target. Researchers now know that analog and in-memory systems can achieve extraordinary efficiency under certain conditions. Competitors can investigate the same approach. Manufacturers can experiment with larger designs. Software engineers can begin building tools around them. And suddenly, an abandoned area of computing research becomes strategically interesting again. The most likely future is not one where analog chips suddenly replace Nvidia GPUs next year. Technology rarely changes that cleanly. Instead, these systems would probably appear first in specialized applications: wireless signal processing, specific inference workloads, scientific calculations, problems where the mathematics is predictable and the architecture can be heavily optimized for one task. That is much easier than replacing a general AI accelerator. Then, if the technology scales, the scope could expand, and Nvidia will almost certainly not stand still. The company has survived multiple technological shifts precisely because it invests aggressively in the technologies surrounding accelerated computing. AMD, Intel, Google, Amazon, and other semiconductor companies are also researching ways to move computation closer to memory and reduce energy consumption. So the real competition may not ultimately be China's analog chip versus Nvidia. It could become something broader: digital computing versus increasingly hybrid architectures, processing versus in-memory computing, brute force scale versus efficiency, and behind all of it sits an uncomfortable reality. Artificial intelligence cannot keep demanding exponentially larger amounts of electricity forever. Something has to change. The models, the hardware, the data centers, or all three. For the last decade, the industry's solution has largely been to build more GPUs. More servers, more cooling, more power, more data centers. But Sun's experiment asks a much more interesting question. What if instead of giving AI more electricity, we changed how computers calculate? There is something almost circular about this story. Computing began with physical machines, gears, currents, voltages, mechanical relationships. Then digital technology replaced them. Ones and zeros were cleaner, more reliable, more scalable. And for half a century, they won so completely that analog computing practically disappeared from mainstream computer science. Then, we built artificial intelligence. The calculations became enormous, the energy requirements became enormous, and suddenly, some of the weaknesses of digital computing became impossible to ignore. So researchers went searching for another solution and found themselves reopening a door the industry closed 50 years ago. Maybe this Chinese chip becomes commercially important. Maybe it remains a specialized accelerator. Maybe manufacturing problems prevent it from scaling. Maybe the 1,000 times advantage collapses when engineers try to train genuinely enormous AI models. All of those outcomes are still possible. But that's not really what makes this research interesting. The important part is that one of the fundamental assumptions behind modern computing has been challenged. For decades, analog computing was treated as something humanity had already tried and rejected. Too noisy, too unreliable, too difficult to scale. Now, researchers have demonstrated that with modern memory technology and a completely different approach to correcting errors, some of those old limitations may no longer be absolute. And if that idea survives the transition from a laboratory in Beijing to real-world hardware, then Nvidia may eventually have a much bigger problem than another competitor. Because competitors can be beaten, prices can be lowered, GPUs can be made faster, but it is much harder to defend a technological empire when someone discovers that the industry may no longer need to play by the same rules. For now, Nvidia still dominates AI computing. Its ecosystem remains enormous. Its GPUs remain essential. And China's analog processor is still an experimental technology with major questions left unanswered. But somewhere inside a Beijing laboratory, researchers just demonstrated something the computer industry spent decades believing wasn't practical. They made analog computing precise. They made it extraordinarily efficient, and they built it using technology that could potentially be manufactured at scale. The GPU isn't obsolete, not yet, but for the first time in a long time, there may be another way.